scaling. We just want to talk about some horizontal scaling happening here. So in this type of problem, they're telling you what kind of scaling is happening. This is called a horizontal scaling, and so that means this graph, the f, is being shrunk or it's being stretched horizontally. Okay, now because it's horizontally happening, we know that we're dealing with the b. Okay, when we're talking about transformations, we have the a, the b, the h, and the k. All right, the a is a number that scales the function, and it scales the function vertically. The b scales the function horizontally. And then the h and the k, they both shift the function. They don't stretch or shrink the function at all. Now, because this is a quadratic function, really quick, I want to show you guys what a quadratic function looks like with each of these letters. Okay, we can have an a times x squared, or we can have a x or b times x squared. That's where the b is. We can have an x squared plus k, or we have an x minus h squared. Okay, and altogether what that looks like is a times b x minus h squared plus k. Wow, that's a lot of stuff. A lot of stuff that can happen to an x squared function. An x squared function, as you guys know, is a parent function. I like to call them the mother function. Okay, so these four numbers are all the different transformations that the x squared can undergo. Okay, back to the b. Okay, I know I wrote this b cursive and this b not cursive. Sorry about that. But if we have a b that's greater than 1, that's going to be a Hori, what do you call it? A Hori scale. And if a b is greater or less than 1 but greater than 0, that is also a Hori scale. The first one is a shrink, and the second one is a stretch, which is kind of weird. Like, you wouldn't think that if your b is greater than 1 that it's a shrink, but it is. It's a shrink. Whenever something is happening to the x inside the group, and that includes the b or the h, you always kind of have to think the opposite, okay? And let me explain to you guys what that means. Now, the a and the k are different. You don't have to think the opposite when you think about those. Like with the a, if I put the a right here instead of the b, this would be a vertical stretch because, the number is bigger than 1, so it would stretch the function instead of shrink it. Okay, so anyways, let's go on. We know that we're dealing with a b here, and so what we're going to do first is we're going to identify 2 points. Now, you really only need 2 points, and that would be, actually, this is 1 point, the point that changes to the other one. And since it's a Hori scaling, we know that the x value is going to be the value that changes. You see the 3 stays the same. The y values will just stay the same, but the x values will change. Let's go ahead and pick another 2 points just for good measure. This point looks like it's 7, 0, and this one right here is 3.50. Okay, so the 4 goes to a 2 and the 7 goes to a 5, right? We're starting with the 4 and we're scaling it to a 2. So it goes from a 4 to a 2, and the 7 goes from a 7 to a 3.5. Now when we're scaling, we're multiplying. What can you multiply the 4 to in order to get a 2? And if you thought 1/2, you were right. If we multiply the 4 by 1/2, that scales it to a 2. If we multiply the 7 by 1/2, that scales it to a 3.5. Now remember how I said you had to think the inverse or the opposite when you're thinking about the b? So what we would do is we would write the inverse of the 1/2. And the inverse of the 1/2 is 2. And so that means our answer is going to be f of 2x. That's how you would write g as a function of f, or in terms of f. That's how they write it right here. And really quick, I want to show you guys why this works. Okay, so if I have a g, and if I plug in a 2, what am I supposed to get? If I plug in a 2, I'm supposed to get a 3, okay? Because this red line is the g. So if I plug in 2, I should get 3. So let's go with our definition right here. I'm going to go f of 2 times 2. Okay, so you see the 2 that I plugged in. This is the 2 that I plugged in. Okay, and then after I go 2 times 2, what do I get? I get 4. So now I have f of 4. And now if I want to know what f of 4 is, I'm going to go over to my f function, which is this blue line. If I go over to x equals 4, I get 3. And so that means I get 3. Okay, which is exactly what we wanted. We wanted a 3 to prove ourselves right. We could also do that with the 3.5. If we plug 3.5 in right here, hopefully we would get a 7, so then we would get a 0, so then this point would work too. So you see how that works? This has to be a 2, not a 1/2, because when we plug in the x, it has to multiply to it in order to scale back up to the 4, so we get the 3 for that point. So anyways, the b is the worst one out of the 4. The b, we have to think the inverse, and the b is the one that is a scaling one. And the scaling numbers are a little more complicated than the shifting ones.